Welcome back to ClearSpot. 30 years ago, managing a solar farm meant walking the site with a clipboard and a pen. Today, a solar farm can manage itself, detect problems before they happen, optimize itself in real time, make decisions faster than a human operator ever could. That didn't happen overnight. It's the result of 3 decades of evolution, each generation solving problems the previous one couldn't. In this video, we're going to trace that evolution, from SCADA systems that were revolutionary in their time, to autonomous decision-making that's reshaping the industry right now. And more importantly, we're going to show you what this evolution means for solar farms today, and where it's headed next. Let's dive in. Let's start at the beginning. The first solar farms, and I'm talking the 1990s and early 2000s, relied almost entirely on manual monitoring. Here's how it worked. A technician would walk the site once a day, sometimes twice a week. They'd visually inspect panels, check inverter lights, note any obvious problems. They'd record their observations on paper, or if they were high-tech, a clipboard with a form. Then they'd report back to the office. Management would review. If something looked wrong, they'd send a repair crew. Sound slow? It was. A problem that occurred on Monday might not be detected until Friday. By then, days of lost generation. But here's what's important to understand. This was actually an improvement. Before solar farms, nobody monitored anything in real time. This was state-of-the-art. It was progress. Problem it solved. No visibility into performance. At least now, there was some visibility, even if it was delayed. Problem it created. Problem 1. Detection lag. Problems weren't detected for days or weeks. Problem 2. Inconsistency. Different technicians would notice different things. No standardized reporting. Problem 3. Scalability. Managing 100 panels? Fine. Managing 10,000 panels. You'd need an army of technicians. Problem 4. Missed problems. A technician could walk past a failing module and never notice. Human eyes can't catch everything. By the late 1990s, it was clear you couldn't scale solar without better monitoring. Enter SCADA. SCADA stands for Supervisory Control and Data Acquisition. The acronym is boring. The innovation was revolutionary. Here's what SCADA did. Instead of a technician walking the site, sensors installed throughout the solar farm constantly monitored conditions. Inverter output, string voltage, temperature, irradiance, all that data streamed back to a central monitoring system, in real time, or near real time. Now, when something went wrong, a dashboard could show it immediately. An alert would trigger. An operator would see it. They'd send a technician out, often, same day, not days later. This was huge. Solar became scalable. You could manage 1 gigawatt from a single control room. Problem it solved. 1. Real-time visibility. You could see what was happening right now, not 3 days ago. 2. Faster response. From days of downtime to hours. 3. Scalability. 1 operator could monitor 50-plus sites. Impossible with manual inspection. 4. Data. For the first time, solar farms generated quantitative performance data instead of qualitative observations. SCADA was transformative, and it's still the backbone of most solar operations today. But, and this is important, SCADA had a fundamental limitation. SCADA was reactive. It detected problems after they happened. Here's what I mean. A bypass diode fails. For a few hours, the system operates with the failure, generating less power. Then, a sensor picks up the anomaly. An alert fires. An operator sees the alert and sends a technician. By then, several hours of lost generation. More importantly, SCADA couldn't predict. It could tell you something was wrong. It couldn't tell you something would go wrong tomorrow. A module was degrading. SCADA wouldn't catch it until degradation was already happening and affecting output. A bearing was wearing out. SCADA might show elevated temperature but couldn't predict failure before catastrophe. Here's the other limitation. SCADA operated on pre-programmed rules. If output dropped below 60% of expected alert, if temperature exceeded 75 degrees, alert. These were binary thresholds. If, then rules. What if output dropped to 58% because of temporary cloud cover, but the rule was set to 60%? You'd get false alarms. What if it's 74 degrees inside the inverter, but external temperature is 110 degrees? Completely normal. The sensor might flag it anyway. The industry called this alert fatigue. Too many alerts for things that don't matter. Operators learned to ignore alerts. The challenge: SCADA could see what was happening. It couldn't understand why it was happening or what would happen next. It was like having security cameras, but no security guards who could interpret the footage. So by the 2010s, even as SCADA became more sophisticated, a new question emerged. What if the system didn't just detect problems? What if it predicted them? What if it didn't just report what happened? What if it decided what to do about it? That question led to the third era. Autonomous decision-making is what happens when you layer machine learning and AI on top of the data infrastructure that SCADA built. Here's the fundamental difference. SCADA says, your output is 58% of expected. Alert operator. Autonomous systems say, your output is 58% of expected. That's normal for this time of year, this weather pattern given the panel age, but if output drops to 50% by Tuesday, that indicates a module failure pattern we've seen before. Let's predict failure in 10 days. Let's schedule maintenance for day 5, before peak loads. That saves X dollars in revenue protection. Decision made. All of that, perception, analysis, decision-making, happens in milliseconds. Let me break down what that actually means. Perceive. The system ingests data from multiple sources simultaneously, not just inverter output. Also, weather data, historical performance, module age, dust levels, grid conditions, equipment maintenance history, even satellite imagery of the site. It builds a comprehensive real-time model of what's happening. Analyze. The system applies machine learning models to identify patterns. It's not looking for simple threshold violations. It's looking for anomalies, unexpected deviations from normal behavior given the current context. Is 58% output bad? Maybe, maybe not. The autonomous system knows it depends on 47 different factors. It weighs all 47. Decide. The system evaluates multiple potential responses. Option 1. Send technician to inspect. Cost, $500. Time, 4 hours. Option 2. Schedule preventive cleaning. Cost, $300. Time, 2 hours. Option 3. Adjust inverter configuration temporarily. Cost, $0. Time, immediate. Option 4. Wait 24 hours and reassess. Cost, $0. Time, 24 hours. Risk. Revenue loss continues. The system calculates expected outcome of each option, chooses the one that maximizes value while minimizing cost and risk. Act. Once decided, the system executes. No human approval needed, no waiting for a manager to review the recommendation. The action happens immediately, or is scheduled optimally. Now here's what's transformative. The system learns from outcomes. If it decided to clean panels on day 3 and that recovered $2,000 in revenue, the system remembers. Next time it sees similar patterns, it weights that decision higher. The system gets smarter. That doesn't happen with SCADA. SCADA's rules are static unless a programmer rewrites them. Autonomous systems learn continuously. What problem does this solve? 1. Predictive power. You see failures coming, not after they happen. That's days or weeks of advance warning. 2. Optimal decision-making. You're not following pre-programmed rules. You're making contextual, cost-aware decisions. Each decision is individually optimized. 3. Speed, milliseconds versus hours versus days. When grid conditions demand sub-second responses, only autonomous systems respond fast enough. 4. Learning. The system improves over time without programmer intervention. 5. Scalability. One autonomous system can manage 500 sites, learning from all of them simultaneously. SCADA with 500 sites. That's 500 sets of rules to maintain. But here's what's crucial to understand. Autonomous decision-making doesn't replace SCADA. It builds on it. The data infrastructure SCADA created. Autonomous systems depend on it. The sensors, the real-time streaming, the dashboards, all still there. Autonomous systems are a layer on top. They take SCADA's raw data and add intelligence to it. Let me show you how this evolution plays out in a real scenario. A failing bypass diode. Manual era, 1990s to 2000s. Day 1, Monday. Bypass diode fails. Farm loses generation. Day 3, Wednesday. Technician walks site. Visually inspects. Spots nothing. Bypass diodes are small and not obviously broken. Day 10, Wednesday of next week. Routine maintenance crew finds it during planned inspection. Total downtime, 10 days. Revenue loss, $8,000. SCADA era, 2000s to 2020s. Day 1, Monday, 2 p.m. Bypass, diode fails, farm loses generation. Day 1, Monday, 2:15 p.m. String level monitor detects 15% drop on string A. Alert fires. Day 1, Monday, 2:45 p.m. Operator sees alert, dispatches technician. Day 1, Monday, 4 p.m. Technician arrives, repairs bypass diode. Total downtime, 2 hours. Revenue loss, $400. Autonomous era, 2020s and beyond. Day 0, Sunday, autonomous system analyzes data. String A has been showing degradation for 2 weeks. Not enough to trigger SCADA alerts, but a pattern the autonomous system recognizes as pre-failure. Prediction: bypass, diode failure. Probability: 87% within 7 days. Decision: schedule preventive bypass, diode replacement for Day 2, Tuesday, which is a scheduled maintenance day anyway. Maintenance crew is already coming, cost increase $0. Day 2, Tuesday, during routine maintenance bypass diode is replaced. No unplanned downtime, no revenue loss. That's the evolution. From weeks of downtime, to hours, to 0 unplanned downtime. And that's just one component. Multiply this across hundreds of systems on a solar farm, thousands of data points, and you start to see why autonomous decision-making is transformative. So, what becomes possible when you have autonomous decision-making? Scenario 1. Portfolio-wide optimization. Instead of managing each site independently, autonomous systems manage a portfolio holistically. A dust storm is forecast for Region A. Region B has clear skies. Maintenance crews are scheduled for both regions. The autonomous system repositions crews from Region A to Region B. Scheduling, logistics, everything. Why? Because its predicted dust will cost Region A $30,000 in revenue, but repositioning crews to Region B to do preventive cleaning will earn $50,000. Net gain, $20,000. A human scheduler might not see that optimization. An autonomous system does, automatically. Scenario 2. Grid-ready response. The grid requests curtailment. Reduce output by 40% for the next 2 hours. SCADA systems. Acknowledged, reducing inverter settings to 60%. Autonomous systems. Acknowledged, calculating optimal response. Reduce inverter output by 40%. Simultaneously dispatch excess capacity to battery storage if available. Increase efficiency on non-curtailed strings. Prepare to rapid ramp up when curtailment ends. Adjust thermal management to minimize panel degradation during curtailment, all while maximizing revenue potential during and after curtailment. It weighs every variable, executes the globally optimal response, not just the straightforward one. Scenario 3. Autonomous maintenance scheduling. Instead of calendar-based maintenance, we service every quarter 3. Maintenance is condition-based and predictive. Autonomous system knows every bearing, every capacitor, every connection. It predicts which ones will fail next. It schedules maintenance with pinpoint accuracy. You do maintenance when you need to, not when the calendar says. That could mean going 6 months without unnecessary maintenance, or doing maintenance every 3 months if that's what's needed. Result: maintenance costs drop 20 to 40%, unplanned downtime drops 70 to 90%. Scenario 4. Real-time performance tuning. Cloud cover moves across your farm. String A gets shaded for 20 minutes. Meanwhile, string C is in full sun. SCADA systems output on string A dropped. Alert. Autonomous systems. Output on string A dropped due to cloud cover. This is predictable. In 18 minutes, cloud will clear. Meanwhile, to maintain grid stability, increase output on strings B and C within safe thermal limits. Then prepare strings B and C to reduce load when string A comes back online to avoid voltage spike. All of this coordinated across the string, the inverter, and the whole site level, in real time. These aren't hypothetical. These are things autonomous systems are already doing in 2025, and they're the future of how solar farms will operate. Here's what we've covered. Manual monitoring gave us visibility but was slow. SCADA gave us real-time data but was reactive. Autonomous decision-making gives us prediction, optimization, and learning in real time. Each generation solved problems the previous one couldn't. Each generation enabled new possibilities. The evolution didn't stop at SCADA. It's not stopping at autonomous decision-making either. The next frontier is multi-agent orchestration, where different autonomous systems coordinate across interconnected sites and grids. But that's a topic for the next video. For now, understand this. If your solar farm is still using purely SCADA-based monitoring, you're leaving 5 to 15% of potential value on the table. Autonomous systems aren't the future, they're the present, and they're becoming essential. Like, share, and subscribe for more solar insights. ClearSpot, smart device, smarter decisions.